If you look at the recent Boost Proto library, it uses similar way of doing it. That is, it decouples construction of the expression and its evaluation, which allow you to have multiple evaluation engines. So with the same language or with and subset of, let's say, keywords, you could have a language for variational formulation or, let's say, automatic differentiation, and have different contexts that can be applied in order to evaluate the expression. The nice thing about having the code in C++ is that you use C++ to optimize your language. For example, in FEM, with an interpreted language, what you need to do at some point is to optimize the evaluation of the evaluation of your expression tree, right? And so you need to re-implement many features that are available already in compilers, but you won't be able to go as far as what people are doing in the most prominent compilers. So here we use, just listing two types of optimization that are being used, but typically redundant calculation are optimized away, and expression at compile time are also optimized away. A lot of computation are done at compile time, and decision making are done at compile time. The price to pay is that compilation time, depending on the complexity, can be relatively high.
Can you give an example of a redundant calculation that you're letting the C++ compiler do away with?
But typically, if you have an expression that is present in many, in different part of, if you have one expression, a sub-expression which is present in several times.
Common sub-expression elimination?
Yeah, typically that would be that.
GCC doesn't do that very well, does it?
But from the very small test I did, it was relatively good. Now I've not done a thorough study, but from what I tested, it was relatively good. Yeah. So basically, we do as much as we can at the compile time. We do all kind of computation, and then we generate the code afterwards that will be run at runtime. Yeah, so I've already talked about that. This is another example. So I've brushed the main features or concept that we have in life, and I'm going to present some of our application. This is a work by Gonzalo Peña, basically. I'm going to present his work on Navier-Stokes in moving domains and some application in free structure. So I will have, I think, to go relatively quickly. I'm sure you are all aware of this. So we started with just Navier-Stokes in fixed domain, and we just wanted to check different kind of ways of approximating our problem, like Q2, Q2 minus 2, Q2, Q2 minus 2, but discontinuous, so pressure is discontinuous here. The equivalent, so this is on hypercubes and this is on simplices. Whenever there is a P, and here this is, this is P also here. So we tested all the spaces, so whenever you need to do a convergence in H, you should use Taylor-Hood, and whenever you do a convergence in polynomial order, you should use QK minus 2. So basically we recovered some known results, but that was interesting to check out. And here there is no restriction on K except for the computational power. Then your algebraic problem reads something like this. Here you have your basically the convection diffusion problem. you have different strategies, either direct solver, at least in 2D, or iterative solver with suitable block preconditioning, or algebraic factorization method. Here I just show, we did all these checks, so it will be available in a few months in Gonzalo Peña's PhD thesis. But I just display the result for the Yoshida, for the algebraic factorization method. So here we are interested in looking at the error in time, and we killed the error in space. So we use P9, P8 finite element for U and P, and then we look at the error in time, and we would like to recover the proper expected theoretical convergence order, and that's what we got. So this is expected by the theory. Okay, so this is work by Quarteroni and Saleri, and they didn't have at the time this framework in order to test it. So now they know that the theoretical results are now been checked, at least numerically, on this setting. So that was a nice application of the life features. Another example here, in this example, we have a high order geometry. So this is a Kovasnai test case. We would like to handle high order geometry. So one part of the domain is a P4 prescribed function. And what we do here is that we would like to have the convergence in H or in N of the drag and lift on this boundary and look at the convergence. So, so we use order 1, 2, and 4 geometry, order for the geometry to approximate the geometry. So P4, when NGO is 4, we have an exact description of the boundary because the prescribed function is P4. And here we look at the convergence slope of the drag and the lift in H. The thing is that it seems here we use P4, P2 for velocity and pressure. When we have order 2 and 4 geometry, we recover the same result. But I think here we need to increase the order for velocity and pressure, like P6, P4. But for the polynomial order test case, it's here we fix H and we increase the polynomial order. So we go up to 18 or 16. And what we see is that, of course, since here and here it's order 1 or order 2 geometry, you have absolutely no convergence, whereas with order 4 you converge nicely and exponentially. Right, so we recovered a nice result. So the next step was to do Navier-Stokes in a moving domain. So I think I will go rather quickly and maybe pass to the result. I think there are already quite a lot of FSI presentation. I don't know if they are all they are all in the ALE framework. Maybe one point is that we propose a construction for high order ALE map. So I'm not going into the details, but basically there's slides which are available here. So if you want to look at them, they show how we construct the high order ALE map. And here you have a numerical results that we used to check that everything was okay. So basically we have, I think, a P6. What we do is that we have a domain moving with a prescribed function, which is of order P4 or P6, I can't remember. Here, so this is the part which is moving, right? And here you have some convergence slope in time for either the direct solver or the Yoshida Q method. So we recover all the expected convergence order with this high order ALE map that we proposed. Okay, so regarding FSI, so now we have to put together, everything together. So we have Navier-Stokes and all the features for Navier-Stokes, various kind of solvers and preconditioners or solving strategies. We have Navier-Stokes in moving domains, eventually high-order geometry. Now we would like to go one step forward and do a free structure interaction. So the fluid model is the one as before. Here W is the domain, the mesh velocity, and here in what the results I will show, basically the structure is 1D. So it's a generalized string model which was proposed in Fabio Nobile's thesis. So it's a 2D, 1D model that we actually use. So here is the full problem.